For those that were gone for IASIS, I'm going to try to catch you up on Euler's method in a few minutes, but what we need to start with is the idea of differential. So let's say the problem we're asked to find is to approximate square roots of 1.2, okay? And let's say we don't have a calculator. Here's the idea behind what we're going to do. Okay, so let's think of this graphically first. I'm going to draw the square root graph, which looks something like this. Okay. And from there, I'm going to pick kind of a convenient point. I'm just going to call it x sub 0, y sub 0. Okay. Once I have that point, what I'm going to do is I'm going to draw the tangent line to that point. So here's the plan. Assuming that I don't have a calculator, instead of calculating 1.2 based on the blue graph, I'm going to actually calculate 1.2 based on the tangent line. Because as long as I stay relatively close, the tangent line and the blue graph are about the same. So remember that the equation of a line by point slope is y minus y1, but in this case y1 I called y sub 0 is equal to m times x minus x1, or x sub 0. Okay. More specifically, if I move over the y sub 0, I get that y is equal to y sub 0, and in calculus, m is given by the derivative of the function at that particular point, and then x minus x sub 0. Okay, so this should be the tangent line equation. So in order to be able to write that, I just need a few pieces here. I need the function, which is square root of x. I need a convenient point for x sub 0, y sub 0 that's around 1.2. So logical choice would be that x sub 0 is 1, because then I can get y sub 0 by plugging in, which is also 1. So square root of 1 is 1, so I'm going to use 1 comma 1. Keep in mind I also need the derivative. So I'm going to need f prime, which if you find it is 1 over 2 radical x. And specifically I need the derivative at x sub 0, which will be 1/2. Okay? So according to the idea of using the tangent line, y is equal to y sub 0, which is 1, plus the slope, which is 1/2, times x minus x sub 0, which is 1. So if I want to approximate 1.2, so for example, assume 1.2 is right here. Okay, 1.2 is right here, then I can just plug that in, 1.2 there. So I get that y is equal to 1 plus 1/2 times 1.2 minus 1. Okay, and I'm going to do something here that doesn't seem useful, but keep in mind we're approximating square root of 1.2. What we're saying, this is about equal to 1 plus 1/2 times 0.2. So if you work that out, that's about 1.1. If you work out the actual value on the calculator of square root of 1.2, you'll see that it's about 1.09. So not bad as long as we stay close. Okay, the reason I did it this way is because I want to point something out. Another way to view this is that y is equal to y sub 0, and another way to write the slope is dy dx. And this right here is what we calculated here, 0.2. So in other words, it's the gap between x sub 0 and 1.2, in that case 1 and 1.2. So that's really like a delta x. That's how far we moved over. Okay, now delta x and dx are sort of the same, so you can actually kind of cancel them. So y is sort of like an initial y plus a change in y, or dy. So the idea behind differentials is I'm going to start at an initial y value and then just move up a certain amount. Okay. So let's do a second example very quickly. Let's say I want to approximate the cube root of 27.5. Okay. I'm going to move fast. So the function is obviously the cube root of x, or x to the 1/3. Okay. A good value to pick is going to be 27, because then if you do that, our y sub 0, cube root of 27 is 3. So we're almost set. I just need the derivative, which if you work it out is going to be 1/3 x to the negative 2/3, which if you plug in 27 looks like this, 1 over 3, 27 to the 2/3. Okay, keep in mind that this is cube root of 27 squared. Okay, the first thing I'm going to do is the cube rooting, and then I'm going to square it, so it looks like the slope is 1 over 27. Okay, so according to the differentials, to get my point slope, y equals y sub 0, the initial point, which is 3, plus my slope, which is 1 over 27, times my delta x, which is the difference between our point in question, 27.5, and the previous point. So this is our delta x. So it's going to be 3 plus 1 over 27 times 0.5. Okay? When you work that out, okay, you get 3.019. It turns out if you work out the cube root of 27 exactly, or cube root of 27.5 exactly, you should get 3.018. So we're pretty close. But the idea here again is it's going to be some slope times delta x, and that's going to be added to your original y value. Okay? So here is what Euler did. Okay. What Euler did is he solved a differential equation by doing the following. So he had an initial point, okay? And then what he did with that initial point is he drew the tangent line at that initial point. And then he moved a certain value, delta x, across and slid up the tangent line. Once he did that, he has a new point now, okay? And he did the same thing. He drew a tangent line at that point, slid up the same delta x, which took you to a new point, okay? And at that point, he did the same thing. He slid over delta x and up a certain distance, delta y. And then he just gets a mesh of points. And although he doesn't have the equation, Euler at least has a graph that passes through those points. So let's understand how that works now. So what Euler did is he just took differentials and he just repeated it. So Euler said to get the next y, you need to take the previous y plus the slope at that point times a delta x. Okay? And he just repeated it over and over and over and over again. So for computer science people, this is iteration recursion. Okay, so again, this is the next y. This right here is the previous y. This right here is the slope specifically of the tangent line. And this right here is the change in x. But put those two together. Remember the delta x and the dx cancel, and that whole entire thing is just delta y or dy. That's really the change in y. Okay? So let's start with a differential equation, and then we're just going to apply Euler's. So let's assume we have the following. Let's say dy dx is equal to, I'll just make up x squared minus y. It turns out this differential equation is not separable, so we have no choice but to use numerical methods. Let's say my initial condition is, I don't know, 0, 1. Okay, so here's what Euler did. The best way to do this is to set up a table. So I'm going to need my coordinates. Next thing I need to calculate for Euler's is I'm going to need to calculate the slope. So I'm going to need to calculate dy dx specifically at the point in question. Okay? And then once I have that, I can apply Euler's. So to get the next y, take my previous y plus the slope times delta x. Okay? So let's apply that. So our first coordinate is 0, 1. If I plug in 0, 1 into the slope formula here, I'm going to get, let's see, 0 minus 1, so I'm going to get negative 1 for my slope. So Euler says to get the next y, which we'll call y1, we take the previous y, which is 1, plus the slope, which is negative 1, and I need a delta x. It turns out we can choose that, so I'm going to pick delta x to just be 0.01. Okay, in the book, I think this is called h, in the book. Okay, so times 0.1, so I should get 1 minus 0.1, which is going to be 0.9. So what does that tell me? That means if I am at 0.1, that means my y value is 0.9. A good thing to do is, since delta x is 0.1, that means we move over 0.1 every time. And so it's a good way to kind of keep track of your x coordinates. Okay, so my new coordinate is 0.1, 0.9. I need to plug that into the slope equation to get my slope. So if I go 0.1 squared minus 0.9, you will get negative 0.89. Okay? So once you have that, to get your next y sub 2, you look at the previous y, which was 0.9. You add the slope you just calculated, which was negative 0.89, and your delta x always stays the same. So when you calculate that, 0.811. So that's your new y value. Okay? So I'm going to take these points, and plug it into my slope again to calculate the slope. And you end up getting negative 0.771. So the next y was your previous y plus the slope you just calculated times your delta x, which always stays the same. Okay? Okay, rounded up to 3 decimals is 0.734. So that's your next y. Okay, and you just keep going and going on like that. So in the book, it'll have something like n equals 10. That means you're going to have to do it 10 times. Okay, hopefully that helps.